isterseniz hocam ben yayında izleyeceğim.
Tamam. Okay, so today what we will look at is linear systems. Linear systems. A linear system on Rn, say on Rn.
Hocam, we can see your screen now.
Oh, I'm
you
sorry.
sharing?
Yeah, I'm sharing, but I have to. I did not. Okay. Yes. Okay, sorry.
Oh, okay.
No, I'm
I
sharing.
think you can.
Yes. Okay.
No,
So,
are you?
am I sharing or?
Give me. No, hocam, we can't see again.
Okay,
now see.
now?
Okay, now we can see.
Okay.
Okay.
On Rn. So what we really have is something like this. We have. So that is. We have n linear equations with n unknowns. So it's something like this, dx1 dt equals a1 x1 plus a2 plus b1 x2 plus say, okay, let's use good letters, d1 xn dx2 dt equals a2 x1 plus b2 x2 plus, anyway, I'm calling this letter d2 xn, and then dxn, and finally dxn dt equals an x1 plus this was d2 dn xn. Now you can write this as a vector equation, You can write this as a vector equation like this: d by dt of the vector x1, x2, xn is just this right-hand side, but the right-hand side you can write it as a matrix times x1, x2, xn. So this would be like the matrix A1, B1, D1, A2, B2, D2, and so on. Okay, you can write it as a matrix equation. And to write it shortly, you can call x of t as x1 of t, xn of t. This is a vector in Rn. And A is a matrix. A is an n cross n matrix. This is the matrix A. So the equation, the system becomes dx dt equals A times x. And this is capital X, it's a vector. So I will write vectors as capitals, or if I don't forget, with arrows. Okay, so a linear system is something like this. Okay, this is a linear system. So what does this show? This kind of, so what we really have is like, let's kind of make a little picture. Say we are in Rn, say this is Rn. It's three-dimensional, but let's say this is in Rn. We have a starting point, say x0 vector, which is actually x1, 0, x2, 0, and then xn 0, the starting initial point. And then we look at the equation, and the solution of the equation will give us a curve. We have the solution curve. Actually, not the solution curve. This is the curve. X equals x of t. as a parametrized curve. As a parametric curve. Why is it parametric? Because there's no t-axis. So this is the phase space. Is Rn. So you see that normally I would have another t-axis, but it's kind of difficult to show. And the dynamical system tells us how we move, how this point moves in time. So time is a parameter. Time doesn't really show explicitly, but time is a parameter. Remember the phase portraits we had, the phase pictures we had? That's what exactly is happening. We did this in 2 dimension last time. This we can generalize in 3 dimension. The only thing that is system is linear. Let's kind of look at some examples. And the easiest ones are so-called uncoupled systems. Now, uncoupled, we had that word before. Uncoupled means there's one equation with x1, little x1, one equation with x2, one equation with xn. x1 only, x2 only, and xn only. In other words, there's totally separated, the variables on the right-hand side are separated. So typically, this would look like this: dx1 dt equals, say, a times x1. dx2 dt would be b times x2. dx3 dt equals c times x3, and so on. So this is only x3, only x2, etc. This is such systems are called totally uncoupled. And basically this is just an kind of unrelated differential equations. You see, x1 is one differential equation, x2 is another differential equation, and so on. And how do I solve it? If I try to solve it, what do we get? We get x1 is some constant, say c1 e to the at, x2 equals some constant c2 e to the bt, and so on. x3 is some constant c3 e to the ct, and so on. Okay? And we did this in 2x2 case, in 3x3 case. Now, what is the solution curve? The solution curve. You have to use some imagination. You eliminate t, and you get a relation between x1 and x2. Eliminate t, you get a relation between x1 and x3, and so on. So basically, in the x1, x2 plane, say this is x1, x2 plane, you have one curve, that's the shadow. In the x2, x3 plane, you have another curve. In the this is x3. x1, x3 plane, you have another curve. So basically, these are the shadows. The curve itself should be something like this. I don't want to imagine it or draw it, but you can use your imagination. See, because it has 3 components, it's complicated. With 2 components, it's easy because we can sketch easily curves in the plane. Okay? And if I recall some examples with it, easier to see on R2, on the plane. So 2x2 systems. And we had some examples. We had, for example, dx1 dt equals, say, x1, dx2 dt equals 2x2. How did the curve look? Then it would say x1 equals c e to the t, and x2 is c1, c2 e to the 2t. And if you look, x2 is something like some constant x1 square. These are the curves we get. It's easy to eliminate. With 3, it's more difficult to eliminate because you can eliminate only these two. So I can draw these, sketch these. So this is, say, x1, x2. Now there are two particular ones. There's x2 is x1 square. So basically we should have some things like this. And depending on the c, we get different pictures. No, I'm sorry, not the last one, because they all go through the origin, right? Depending on c, it's up there or down there. Now, as a curve in t, so let's sketch the trajectory. So note, as t goes to minus infinity, x1, x2 go to 0. And as t goes to infinity, x1, x2 go to infinity, plus minus infinity, depending on the sign. So basically, the trajectories are like this. These are trajectories. Plus, there is one other trajectory, 0, 0, 0 is a fixed point. That means x1 is identically 0, x2 is identically 0, is a solution. Correct, because the right-hand side is 0, the left-hand side is 0. So these are trajectories. Also, two more special ones. Also, if c1 is equal to 0, we get half x2 axis, only x2, half because it's either going up or going down, so there's this one, and same thing going down. And if c2 equals 0, we get half x1 axis. x1 going this one, x1 going this one. Now, these trajectories don't intersect because their intersection point would be 0, but 0 is not. So a single trajectory is either this or something like this or something like this. You see, I'm making a hole so that there's a point there. Okay, so these are single trajectories. Maybe I shouldn't make these holes, but I should do them better. I should do something like that. This is a trajectory, this is a trajectory, and 0 is a trajectory. Okay, that's the real picture. Right, this goes up, this goes to the side, and this stays fixed. And then you have the other sides. Okay, and there's one going up and one going down. Okay. This was the story of how things were. We had some other examples, some other pictures, but it was essentially one, and then you solve one, then you solve the other, and you try to put them together. Okay, so this is what we did last time. Now, today we want to generalize all these ideas. Now, this is a uncoupled system, so this is easy because this system is uncoupled. Okay, because x1s are on one side, x2s are on the other side. What if it's not uncoupled? So what about, okay, so let's kind of go to the general case, How can we find solutions, some solutions, let's say some solutions to a linear system x dx dt equals a times x, and these are vectors. How can we find a solution to some general linear system? Now, A is some constant matrix, of course. If A is variable, of course, none of this would work. A is just some number. I mean, constant matrix. N cross N, constant matrix. And X is a vector in R. X of T is a vector in R. Okay, everything is n-dimensional. If you don't like it, think of it two-dimensional, doesn't really matter. Now, how can I solve this? How to find? Now, the trick is, think of the one variable case. So dx dt equals lambda x. This had the solution e to the x equals c e to the lambda t. And this is one of the first equations we saw, the easiest one. Now, generalize the same idea, and look for a solution of the form x of t equals lambda e to the, no, I'm sorry, x of t equals e to the lambda t, I'll call it lambda, oh, not x, I'm sorry, lambda t times a vector x0. x0 is some constant vector. Okay, now where does the idea come from? This is e to the lambda t, this is e to the lambda t. There was a constant c here, but we are in R. In Rn, this would be some constant vector. Because solutions, I want a vector. So I want exponential type of vector solutions, if I can find it. Now, what I do is I plug this in, plug it in. So this is dx dt equals ax will give what? Now x is this is constant. You see the derivative of a actually this is something of the form e to the lambda t times x01, x0, x01, x02, x0n. It's a kind of vector like this. Some vector, some constant times this, e to the lambda t. So the variable is here. So the xt would be lambda e to the lambda t times x. And this you want to be equal to a times x0, I'm sorry, lambda e to the lambda x0. And you really want, I want this to be equal to a times e to the lambda t x0. Now, what I can really do is, I can take, this is the same as e to the lambda t, a times x0. That's the big thing of linear systems, because the constant just moves out. You see the linear system was something like this, a1, a2, an. Remember in the beginning, all these constants in front of x just move to the very out because they're all the same constant. So this is really good. What I really get is, this gives me that x0 and lambda should satisfy, if you cancel the e to the lambda, a times x0 equals lambda x0. And I want x0 different from 0, because x0 equals 0 won't give me something. I want something really original. x0 equals 0 gives me the trivial solution. I want x0 equals 0. Such problems, this is called an eigenvalue problem. Problem in linear algebra. So determining, so what my question is, determine lambda and x0 different from 0, so that A x0 equals lambda x0. This is called an x0 is called an eigenvector. An eigenvector. Lambda is called an eigenvalue. These funny names come from German. Eigen means special. So special vectors and special values. But these are extremely useful. Now, how can I solve this? How do I solve this? Well, what I can do is take it to the left and write it as A minus lambda times identity x0 equals 0. Move everything to the left. Okay? Lambda identity. Identity is this 1 0 1 0 0 0 1 0 0 0 1 matrix. 1 times identity times any vector, it's itself. Write it like this. Now, when you write it like this, you really see this equation. Now, think of linear algebra. This is high school linear algebra. Cool. Linear algebra says that, look at determinant. The determinant of A minus lambda I. If determinant A minus lambda I is different from 0, then this equation, then star has a single solution, unique solution in other words, and this would be x0 equals 0. Because it satisfies, but I want more solutions. So to get some non-zero solution, I should look for lambda so that determinant A minus lambda I equal to 0. Now this thing is called the characteristic equation. Of A. Now, once I find the characteristic equation, once I find the roots of this equation, what is this would be of polynomial of degree n. Because it's an m by n determinant, so, and there's lambda, 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 so it would be lambda to the n. I'll do some examples, easy cases. If I find the roots as lambda 1, lambda 2, lambda n, let's say I find the roots, and then, corresponding vectors, say x0, 1, x0, 2, x0, n, then this gives me solutions x of t equals e to the lambda 1 of t, x0, 1, plus, comma, say call this x1, x2 of t, capital X2, this is vector, equals e to the lambda 2 of t, x0, 2, and so on. This gives me all solutions. Okay. But now a nice thing is, if I have two solutions, the sum of the solutions is also a solution. Then sum of solutions is also a solution. This is because it's linear system. You plug it in, sum of the derivative of a sum is the sum of the derivatives. Derivative of a linear equation is the sum of the linear equations. So you can multiply it out. That means that we can also multiply it out. That means x of t would be some constant c1 e to the lambda 1 t x0 1 plus c2 e to the lambda 2 of t x0 2 plus, say, whatever, will also be a solution. And C1, C2, Cn are just constants. So somehow we are able to get a whole lot of solutions, okay? Now I want to discuss this more clearly on an example. I'm going to give a 2x2 example where I can really do all the computation. Now, if you know linear algebra, this you will say, of course, that's the case, or you remember linear algebra. Usually it's done towards the end of linear algebra. But this is what comes in linear algebra. Now I'll do a 2x2 example, okay? Okay, I'll have an example. And let me kind of be a bit slow because I want to get the numbers right. Okay, so this is this d dt of x1, x2. I'm writing it in 2x2 is just 2x1 plus x2 and 2x1 plus 3x2. I can write this as dx dt equals, this matrix is 2, 1, 2, 3 times x. That's my equation, 2x2 equation. Okay, I want to solve this. Well, to solve this, first find the eigenvalues. For that, I had to look at determinant A minus lambda I. A minus lambda I means determinant of the matrix. Lambda I means lambda I is this one, lambda 0, 0, lambda. So it's diagonal matrix with lambdas. So you get 2 minus lambda, 1, 2, 3 minus lambda. And when you compute that, you get 2 minus lambda, 3 minus lambda, minus 2. And when you work that out, this is lambda squared minus 5 lambda plus 6 minus 2 plus 4. And you realize that this is lambda minus 1, lambda minus 4. I cooked the numbers so something easy comes out. I have this. Now that's nice, that's very nice. Then eigenvalues should be lambda 1 equal to 1 and lambda 2 equal to 4. Because this equal to 0 is the characteristic polynomial. The roots are the eigenvalues. Because we said what were eigenvalues? We said we had to look at this determinant here. You see, we had to look at the determinant A minus lambda I equals 0. The roots would give the characteristic equation. And if you remember, this would be degree n. Here, it's really like a quadratic degree 2. And there are 2 roots, 2 eigenvalues. Now, the next thing is, how do I find eigenvectors? I should say corresponding, because eigenvectors. So I start with lambda 1 equal to 1, and I want to solve A minus I x1 equal to, well, what did we say? x1 0 equal to 0. I want to solve this. Of course, this is a vector, this is a vector. So that really means, what is A minus 1? Let me write it down. A minus 1 is 1, 1, 2, 2, x1, x2. Say, let me call this, say, xy. Let me say x0, 1 is just xy. Xy equals 0, 0. That gives me x plus y equals 0, 2x plus 2y equal to 0. And you see that since the determinant is 0, this does not give a solution, but this implies x, y is equal to negative x. There are many solutions. In fact, you can take x, 0, 1 as the vector 1 minus 1. And actually, all the multiples of it will also be a solution. Okay, so we have one. Now, the next one is, I want to look at lambda equals to 4. So the question becomes a minus 2 minus 4 is negative 2, 1, 2, negative 1, xy equal to 0, 0. This gives minus 2x plus y equal to 0 and 2x minus y equal to 0. So this is just y equal to 2x. So I can take x0, 2 as x is 1, y is 2, or any multiple of it. Okay, so I have found two special solutions. They're not special, but special solutions. x1 of t is, what was it? Lambda was 1, e to the t, lambda is 1. E to the t times 1 minus 1, and x2 of t as e to the 4t times 1 minus 1. No, I'm sorry. x2 is 0, 1, 2. Okay, I have two special solutions, e to the t and e to the 4t. Also, by linearity, instead of 1 minus 1, I could take any multiple. Instead of 1, 2, I could take any multiple, doesn't really matter. So I get x of t will be c1 e to the t 1 minus 1 plus c2 e to the 4t 1, 2 is also a solution. Also a solution. For any c1, c2. c1, c2. It's also a solution. So I have found a lot of solutions. Okay. Now, one thing, are these all the solutions? Well, we'll discuss that later, but this should be all the solutions. But I will discuss that a bit later. But in that case, I have found a lot of solutions. Now, how do I sketch this? Recall, I'm writing this again, x1 of t equals e to the t 1 minus 1, and x2 of t equals e to the 4t 1, 2. These are the two solutions I have. I want to sketch them somehow. Let's see how I can sketch them. Okay, okay. Now, first of all, where is x1? Now, this is x. No, okay. Remember, what was it? I will have the vector x0, 1 was 1 minus 1, and x0, 2 was 1, 2. Where are these vectors? 1 minus 1, so this is okay. And the other one is 1, 2, so it's something like. So I have these two vectors, this and this, okay? And of course, the negative side of it, and then the negative side. So I have two axes, the x1 axis and the x2 axis. x0, 1 axis, x0, 1 axis, and then this is the x0, 2 axis, 2 axes. And what do? I know that along this line, if I start at 0, again, 0, 0 is a fixed point. Do you see that? Because it satisfies d dt of 0, 0 equals a times 0, 0. In fact, that's the only fixed point. And then if I start here, it's going to go up. because here I have e to the 4t, 1, 2. So solutions like this will go up. Now, what about here? Solutions like this will come out. This is e to the 4t, 1 minus 1. Now, if I start, this is c. I put a c because it can go all the way. Now, I can also have this if c is negative. Remember the first pictures? We are not doing with respect to standard x1, x2, but we are doing with respect to this distorted basis. Now, what happens in between? In between, if you kind of look a bit carefully, this is like, I'll try to get it better. Now, what about a solution like x of t equals c1 e to the t. This is e to the t. 1 minus 1 plus c2 e to the 4t, 1, 2. So it's kind of a linear combination of these solutions. So you could do an arrows, but here the velocity is t. Here velocity is, for e to the t, velocity is e to the 4t. So v2 is 4 times v1 to the power 4. So over here, I'm going faster. So what I get is, again, should be kind of use your thing a little. You should get v2 equals v1 to the 4. So you should really get these curves, the 4th power curves. I'm going to justify it soon, but for the time being, believe me. Okay, this would be a guess. And you see, I have the whole phase portrait. This is everything. Why is it everything? Because there is no other space left. And you see, if you look at this picture looks very close to this picture I had here. The only difference is that this is not x1 axis, this is not x2 axis, this is the vx1, 0 vector axis. The other one is the other axis. So this is distorted. The two pictures are almost the same. One is a distortion of the others. Now, it's important to notice that. Okay, if you want, let's stop here for like 10 minutes, and then we'll pick up. I'll try to make this more scientific. Okay. Okay, so we stop for 10 minutes. And if you have any questions, any remarks, please go ahead. Okay, so I'll stop for 10 minutes.
We can hear you. You are muted. I said you are muted.
I'm muted. Okay, sorry. Shall we
Okay.
start?
Yes, yes.
Okay, so it's been 10 minutes. Okay, now what I did here, remember, let me remind you, I kind of just found the eigenvectors, eigenvalues. I was lucky I found two. I computed all of that, and I got these two main directions, the green ones. And of course, it's opposite if you go in the wrong, if you go backwards, and this one and this one. And then I have to have combinations of these two, general case, but the velocity of the first one is e to the t, whereas the velocity is e to the 4t. So the second one is fourth power of the first one. So you should get some curves like this. This was like not very precise, but more or less what it is. Now I'm going to make this precise. Now we will make this precise. We will make this precise. This precise. And it goes and follows. Suppose the matrix A has n eigenvalues, lambda 1, lambda n. Okay, so in other words, that means determinant A minus lambda I is just lambda minus lambda 1, lambda minus lambda 2, and lambda minus lambda n, and n corresponding eigenvectors, say x0, 1, x0, 2, x0, n. Okay, I have n corresponding eigenvectors and n eigenvalues. And suppose, and suppose these, well, eigenvectors, okay. Okay, well, no, let's not suppose that. Then consider, let M be the matrix whose columns are the eigenvectors. So M is something like this. M is this matrix. Here we have x1, 0. Here we have x1, 2, 0. And here we have x and 0. So these are n. These are column vectors. So whose columns are the eigenvectors? So this is an n cross n matrix. And if you multiply A times M, what would that be? Well, if you think of matrix multiplication, this would be A times x0, A times x0, 1, A times x0, 2, A times x0, n. Have you multiply? Because you take this column and multiply by the matrix, A times that. But A times x0, 1 is lambda 1, x0, 1. This one is lambda 2, x0, 2. And this one is lambda n, x0, n. And you can write this as m, this matrix, times the lambda 1, lambda 2, lambda n, 0, 0. You can write it like this. Okay, let's call this D. D is a diagonal matrix. Okay, I'm going to illustrate this in the previous example. Recall in the previous example, I just want to do it so that you believe my computation. A was example. Recall the example where A was 2, 1, 2, 3. Lambda 1 was 1, lambda 2 was 4. X0, 1 was 1, negative 1. X0, 2 was 1, 2. These were the eigenvectors, eigenvalues. So A times, so M is just A times 1, negative 1, 1, 2. So this is just, let me just erase this, and this is what A times M is just 2, 2, 1, 3 times M is these two, 1 minus 1, 1, 2. And when you multiply it, you get 1, 2 times 1 minus 1 is 1. 2, okay, what's happening? Okay, 2 minus 3 is minus 1, and 2 plus 2 is 4, and then 2 plus 6 is 8. And you really see that this is 1 times 1 minus 1, and 4 times 1, 2. So this is really 1 minus 1, 4. 1, 2 times 1, 0, 0, 4. Okay, you get this. This is D. This is D is just the diagonal elements are lambda 1, lambda 2, lambda n, rest is 0. Okay, so what I have done is, so I have written, I have gotten this equation A times M is M times D, or take A inverse, M inverse A M equals D. This is diagonal. Now the question is there an M inverse? M inverse. So is it, and the answer again, linear algebra, yes, if the columns are linearly independent. Linearly independent. And it is yes if, so columns are linearly independent, that is, this is the same as eigenvectors are linearly independent. And this is the same as, this is, let me say, this is true in if all eigenvalues are distinct, and in other cases, but don't worry about that, this is linear algebra. Now again, if you are not very good with linear algebra, think of the vectors I, J, K in space, or Ij in plane. So linearly independent means they generate the whole space. But this is some theorem in linear algebra, and as I said, in reasonable cases, these are all distinct. Then, now, my equation, recall my equation was this. Now, I will do change of variables. And the change of variables is the following. Let y equals m inverse times x, or x equals m times y. Now let's try to write the equation then. dy dt equals m inverse, this is constant, times dx dt. And dx dt is m inverse times ax, because dx dt is ax. Now, m inverse a, but ax is, what is ax? Okay, but what is x? X is equal to my. So m inverse a, m, y. But M inverse AM is D. So I get dy dt equals D times Y. But remember, what was D? D was just the diagonal matrix. So this really says that dy1 dt equals lambda 1 y1, dy2 dt equals lambda 2 y2, and then dy and dt. Okay, no space left. So, and then the others, dy and dt is lambda n yn. So this is uncoupled. So what we have done is, uncoupled the system with new variables y equals m times x. No, I'm sorry. It was y equals m inverse x. And then in that case, dy dt is just lambda 1, lambda 2, lambda n 0, 0 times y. So life in the y space, so that really says that y1 is c1 e to the lambda 1 t, y2 is c2 e to the lambda 2t, and yn is cn e to the lambda n t. So in the y space, things are really easy. Now the difference is, how do you go from the x space to the y space? Well, x space is straight. This is the x space. And to go to the y space, you have this transformation M inverse, which really what it does is basically it distorts the axis. Y1. So this is, say, x1, x2, x3. This will become x3. And then this will become, it's going to be distorted, so it's going to become something like y1, y2, and y3. So in this space, we have like this solution, actually trajectory. And how do we carry it back to our space? Well, to carry it back to our space, we do m times this trajectory will give the trajectory here. But basically, the picture will be just a kind of distortion of the first picture. So the picture in y is just some distortion of the picture in x. Let's go back to our example. What was our example? Remember, let's go back to our example that we did here, this AMA. Okay? Again, looking back at the example, look again at the example, look at the example. With what was that? A was 2, 2, 1, 3. Was it the case? Yes. And lambda 1 was 1, x0, 1 was 1 minus 1, lambda 2 was 4, x0, 2 was 1, 2. And m was, what was m? M we found, we computed m. M was 1 minus 1, 1, 2. And if I put m inverse, well, let's say, if x equals m times y, what does it mean? That means x1 plus x2 equals y1, and minus x1 plus x2 equals y2. And conversely, I can solve y from here. No, I'm sorry, that's the other way around. Okay, no, it's correct. Then if I solve this in these new variables, dx dt equals ax becomes dy1 dt equals y1, dy2 dt equals y2. No, 4y2. Lambda 2 is 4. So that really gives, let's clean again, dy2 dt equals 4y2. This really gives that y1 is equal some constant e to the t, y2 is another constant e to the 4t, or y2 is some constant y1 to the 4th. You see in this y variables, so these are the y variables, y1, y2. In these variables, life is quite easy because I have, again, a fixed point 0. Fixed point is always fixed point. And then what are the trajectories? Well, I have these guys as certain trajectories, these guys, these guys, these guys as certain trajectories. And then I have other trajectories. What are they? Let's kind of do them in green. We have y equals x to the 4, like this, like this, like this, like this. No, I'm sorry, the bottom ones are not correct because it has to be like this, okay, like this, and then you want more. And are these all the solutions? Yes, because there's no other place left. From every point, we have one trajectory passing. Okay, so this is the picture as long as we can do this. So now, I can really go to this 2x2 case and do it a bit properly. So we can back to the 2x2 case. Back to the 2x2 case. What can happen? Well, characteristic equation. Characteristic equation was, what was it? Determinant a minus lambda I equal to 0. That's really like some lambda square plus, say, alpha lambda plus beta equal to 0. This case 1, I have two real roots. Lambda 1, lambda 2. Then I have two eigenvectors, corresponding eigenvectors, x01, x02. Okay? So, and two solutions, that gives me two solutions. Well, before I say that, in the y space, the matrix M is just x01, x02. And you can prove that these are not multiples of one another. Why? Because if you put A to 1, you get lambda 1, A to 2, two real distinct roots, let's say. So lambda 1 is different from lambda 2. So it grows in one side, it's lambda 1 times, the other one is 4 lambda 1, lambda 2 times. So they are not distinct. So something like this, x01 is like this, x02 is something like this. They are like distinct. In that case, M is this. And if I let y equals M inverse X, or X equals My, and since you know M, it's very easy to compute what this is, you know all these numbers, then in Y, we get dy1 dt equals lambda 1 y1 dy2 dt equals lambda 2 y2. Okay, let's say lambda 1 is different from lambda 1, 0, and lambda 2 is different from 0. Let's say none of them are 0. We can think of that again as before. So the only fixed point is 0, 0, is 0, 0. And then you have solutions are solutions x, y1 equals e to the lambda 1 t, some constant, y2 equals another constant e to the lambda 2 t. So that really gives that y2 is just c times y1 to the lambda 2 over lambda 1. Whatever that number is. Okay, you get curves like this. Now these are all the solutions. Y2 is c times y1 lambda 2 over lambda 1. Some power. And they're not the same, so the power is, no, they could be the same. No, they're not the same. Okay, doesn't really matter. Okay, so in that case, what can we expect? Now, case 1 is, okay, let's kind of write down the case 1. Lambda 1 said it's lambda 2. Then what I have is y2 equals c times y1. So what I have is again, one fixed point in the middle, and then the trajectories are straight lines. Because y2 is, okay, these are the trajectories. Lines through the lines from 0, 0, the origin. Now, which way do they go? They go. Now, if lambda 1 equals lambda 2 is positive, away from origin, and if lambda 1 equals lambda 2 is negative, towards the origin. Why is that? Because as t gets larger, remember, y1 was e to the lambda 1 t, and y2 was e to the lambda 2 t. And they are the same, depending, this either goes to the origin or not. So towards the origin, one would be like this, towards the origin. All of them, of course. Or the other way around, all of them. So red or blue. All go towards the origin if lambdas are negative. All move away from the origin if lambdas are positive. This is just tracing the curve. Okay, what else can we expect? Well, what else? What else? Well, we can have lambda 1 is different from lambda 2. So then y2 equals c y1 to the lambda 1 over, no, lambda 2 over lambda 1. So depending on which one is bigger, the curves, well, also, now if lambda 1 and lambda 2 are both plus or both minus, this gives a curve. The curve is c y2 equals c e to the c y1 to some positive number. So then the curves would be something like this. I mean, depending on whether the positive number is bigger than 1 or smaller than 1, the curves will be something like this. This is y1. No, this is y2. This is y1. And if it goes this way, let me write it. It goes this way if both are positive, and it goes the other way if both are negative. Okay, so again, the previous, it looks like, of course, these are also, you have also these trajectories going up or down, and then 0, 0 is again the only fixed point. Okay, there's a third case that may happen, and the third case, or we can have lambda 1 positive and lambda 2 negative, or the other way around, or lambda 1 negative, lambda 2 positive. The pictures are more or less the same, so I don't really care. Then, in that case, y1 is c1 e to the positive lambda 1 t, y2 is c e to the c2 e to the lambda 2 t. So now as t goes to minus infinity, y1 goes to 0, but y2 goes to infinity. And as t goes to infinity, this time y1 goes to infinity, but y2 goes to 0. So the signs are different. So what happens? Let's see. What can we have? Let's try to see what we can have. Okay, again, we have the axis. And then in general, in general, y2 will be some constant times y1 to a negative power. Because lambda 2 over lambda 1 will be a negative power. Oh, well, again, 0 is 0, is a fixed point. Then I have these 4 lines. Say, okay, this, let's kind of give them names. This is y1, this is y2. We said lambda 1 is positive, lambda 2 is negative. I'm looking at that. So basically, over this axis, okay, I have these guys going away, correct? And then, but I have these guys going towards the origin. You see, y2 goes to 0 as t goes to infinity. So this is as t moves, it gets closer to the origin, whereas the others move away from the origin. And in general, what sort of curves do I have? Well, in general, I have y2 is y1 to a negative power. So I would get a picture like this. And which way would these go? Well, y1 gets smaller, but y2 gets bigger. y2 gets smaller, y1 gets bigger. So these would be the trajectories, like hyperbolas. Okay, this is in the y space. What happens in the x space? Let's kind of discuss shortly what happens in the x space. So x is just m times y. The picture in the x space is a distortion, kind of linear distortion. So basically, you kind of squeeze the. So what you would have is something like this. This is x1, x2. But here you have your imaginary, let's kind of say. Here you have your, say, this is the y1, y2, and say this is the y1. Doesn't have to be the same. So you would carry this picture here. Now the fixed point is 0, 0. It doesn't change. Fixed point doesn't change. Now the green goes like this and like that. And the blue comes like this and like that. And then you have these red ones that kind of go like this. You see, this is the X picture. It's a distortion of the same picture, but it's essentially the same picture. Now we have almost done everything except like 1 or 2 cases. What is left? What else may happen? Well, sadly, one can have complex roots for determinant a minus lambda I equal to 0. Complex roots means, so lambda 1 would be, say, I don't know, alpha 1 plus I beta 1. Lambda 2 will be alpha 1 plus, let me write it like this. Alpha plus I beta, but then lambda 2 will be alpha minus I beta. Why? Because determinant A minus lambda I is equals 0 is a real quadratic. So that means complex roots have to be, must be conjugates. Because the root formula says lambda I equals something plus minus square root of this. If this is complex, then you get plus or minus I beta. Okay, in this case, now I'm not going to go through the details, but in this case, we can find another transformation. Another transformation such that I don't want to say that. Okay, I don't want to say this because I want to make simple. Okay, let's just write what would come out. So again, forgetting that we are working with reals. Let's find the eigenvectors, find the eigenvectors. x0, 1 and x0, 2. But note that these will be, these will be complex valued. When you do this, these will be complex valued because a x0, 1 equals alpha plus I beta x0, 1 and b x0, no, a x0, 2 will be alpha minus I beta x0, 2. I'll get some funny thing like that, okay? Now what I can really do is I can separate, okay. So, but forget that I do anything. In that case, I get solutions as x0, 1 equals, let's just write it, some constant c times, I'm not going to write the c, e to the lambda 1, x0, 1, which is e to the alpha plus I beta t x0, 1, x, okay, and the right-hand side is not x0, 1, but x1 of t, and x2 of t will be e to the alpha minus I beta t x0, 2. Now, if you write these in terms, now e to the alpha plus I beta t and e to the alpha minus I beta t can be written as e to the alpha t cos beta t plus I sine beta t. And the other one is minus I sine beta t. And the other one is e to the alpha t cos beta t minus I sine beta t. Now, if you have one solution like this, one solution like that, and then what you really try to do is take the real parts. You can, if you write it down, you'll see how to manipulate, taking real and imaginary parts of these solutions. Again, we get two new solutions, new real solutions that looks like this, that x of, say, x bar 1 of t is e to the alpha t cosine beta t times a vector x bar 1, 0, x bar 1, and x2 of t equals e to the alpha t sine beta t x2 bar. We get two solutions like this. Again, taking real parts and so on, I'm simplifying the thing, but I just want to see what this does. Now, case 1. If alpha is 0, so lambda 1, lambda 2 are plus or minus I beta, pure imaginary. My curve is x1 bar of t equals cos beta t, x1 bar, and x2 bar of t equals sine beta t, x little x2 bar. I have this. But now if you look at this, this says that x1 bar square plus x2 bar square equals cosine plus sine is 1, some x1 0. This was x1 0, this was x2 0, x0 1 bar square plus x0 bar 2 square. So what I get in the x1, x2 plane is circles. And then this is a fixed point. These are circles of radius x0 1 square plus x0 2 square in square root. Of course, I've oversimplified. Next time we can solve an explicit example and so on. And how do they turn? Well, depending on which part you choose, they can turn like this or like that, but they go around the origin as circles. Now, distorted, if distorted, these circles may become ellipses. So how would they be? It would be ellipses, but they're all kind of more or less the same. So that would have an ellipse, another ellipse, another ellipse. But okay, so these ellipses have to be all similar to one another. Okay, so it would be ellipses. They all have to be the same, though. I checked it a bit bad. These concentric ellipses, and 0, 0 is the common. If distorted a bit more, these may become ellipses like this, if you depend on how you turn. But basically, you have ellipses one way or the other one. So this would be, in that case, the changing variables. This would be the y1 axis, this would be the y2 axis. That's a possibility. This is another possibility. Now, case 2, say y1 is, or say, okay, case 2, x1 bar is e to the alpha t cosine beta t times some constant, x1, 0 bar. x2 bar is e to the alpha t sine beta t times x1, x2, 0 bar. And alpha is different from 0. What sort of a picture do I get? Now, in this case, cos beta t sine beta t will make times x0, x1 will make an ellipse or a circle. Depends if you have x0, 1 here and x0, 2 here, will make an ellipse or a circle, whether you have it or not. But e to the alpha t makes sure that the radius changes in time. So this would get a spiral. And you could have pictures like, finish it, you could have pictures like, okay, that's kind of, now again, 0, 0 is a fixed point. That's something. So we could have pictures like this, spiraling around the origin. And what is the possibility? So this is e to the alpha t times cosine beta t times, say, x0, x0, 1, sine beta t times x0, 2. So ellipses, but this is the radius. Now, if alpha is positive, gets away from the origin, so the ellipses will kind of curve outside. And if alpha is negative, gets towards the origin. So if alpha is negative, the picture is totally the opposite. So this is opposite picture. Again, you will say, how does it turn? It turns to the counterclockwise, clockwise. That really depends on how to choose beta. If you choose beta positive, it goes one way. It goes counterclockwise. Otherwise, it will go clockwise. So it's really like your choice of how you choose beta positive or negative, and alpha positive. That is not determined by the equation, because you can have positive beta or negative beta. Doesn't really matter. But you see, you really get all these pictures. Now, there are more cases, but I'm not going to discuss them. But I want to add to one more thing. Classification of the fixed point. Classification of the fixed point. What does it mean? Classification of the fixed point is this. Now, in general, we had eigenvalues. Let me write them, say, case 1. Lambda 1 is positive, lambda 2 is positive. Then e to the lambda I t goes to infinity as t goes to infinity, which said that trajectories move away from the origin. And roughly the picture was like that. And actually, it's not just trajectories, all trajectories. All trajectories move away from the origin. Okay, and this last one is wrong here again, because they move away from the origin. It's kind of going down. Okay, now in case 2, now we call this repeller. 0, 0 is a repeller. Remember, repeller was, there's a fixed point here, but anything close gets far away. Case 2 is lambda 1 is negative, lambda 2 is negative. In that case, how is the picture? Well, the picture would be the similar picture, but this time the arrows go towards the origin. As t goes to infinity, x of t goes to the origin. Okay, so in this case, this one is called 0, 0 is an attractor. And of course, we have case 3, where say lambda 1 is positive, lambda 2 is negative. Remember what the pictures we were getting were these. Again, you have a fixed point. You are getting pictures like this. Lambda 1 is positive, say, so okay, it kind of, well, this was moving here, this was, you had one moving down, one moving up, but these were moving away, these were moving away, and then they were going like that. So this is called a saddle point. It's not attractor only from one line. It's an attractor, the y-axis, not repeller. Attractor only on one line, repel only on another line, one line. But all the others are kind of get close and get far. So this is called the saddle point. It's like the calculus saddle points. So these are the things. What else do we have? We have two more. We had then case 3. If case 3, lambda equals alpha plus or minus beta, lambda 1 and 2 are eigenvalues, complex eigenvalues. So if alpha equals 0, what we get, the trajectory was, remember, were like ellipses. Ellipses. In some sense, is it an attractor? It's not an attractor. Not a repeller. It doesn't push away, but stable, but it's stable. Stable in the sense that if things are close enough, they kind of stay close. If things are far, they stay far. Now, the other thing is if alpha is positive, remember we had spirals moving away from origin. So we had pictures like this. So this is a repeller. Of course, how would the second orbit be? Well, it's kind of should be, you should be able to place all these things next to one another. And then again, if alpha is negative, spiral getting close to 0, 0, because we have to factor e to the alpha t times something. So in this case, the picture would be, okay, let's see, how does it do? Well, it kind of comes like this. Again, does it turn towards clockwise, counterclockwise? That really depends on your choice of pattern. So this is a attractor. Now, if you want to summarize all this, summary, if you want to summarize, and that's quite important in this business, summary, to summarize, right? If all eigenvalues, if for all eigenvalues, real part of lambda is positive, real part. If they are real, implies repeller. because e to the alpha t or e to the lambda t goes to infinity as t goes to infinity. If real lambda is negative for all eigenvalues, it's an attractor. If real lambda equals 0 for all eigenvalues, then it is stable. Okay, so by looking at real by looking at the eigenvalues, we can really check stability. Now, I think I will stop here. Now, this has many applications in real life. Maybe I should problems. I'll give an example. And example is this. Look at an equation like this. Look at the x squared. I'm sorry. D squared x dt squared plus a times dx dt plus b times x equals 0. Let's just look at this equation. This could be the equation of a spring physics. B equals spring constant. B is the spring constant, and A is just friction. So what you have is a spring like this. Now let me draw a proper string. This end is fixed. Okay, and then this kind of, if you push it back and forth, it moves, it kind of oscillates. And this is physics because this is the spring force. And this one is the friction term. This is all of that, you can find it in any high school physics book and so on. Now, we put x1 equals x and x2 as dx dt. Then what was my equation? My equation is d squared x dt squared plus a dx dt plus bx equals 0 becomes dx1 dt is dx dt, that's x2, and dx2 dt is, let me write a parenthesis here, okay, let me write it like this. That is x2, this is dx dt, and that is equal to x2, and dx2 dt is d squared x dt squared, second derivative, and that is equal to minus a dx dt minus bx, and that's equal to minus a x2 minus b x1. So what I have is, to summarize, I have a system dx1 dt equals x2, dx2 dt equals minus bx1 minus ax2. This is a 2 by 2 system, linear system. And knowing how this behaves, 0, 0 is the fixed point, and knowing that how this behaves will solve a true physical problem. Now, this we will look at later when we do examples. This is one of the most basic examples we will see. Depending on the constants A and B, we can say this is a stable system. All the spring forces kind of come down to 0, because what does it mean for x1 and x2 to go to 0? x1 goes to 0 because of friction, x2, the velocity goes to 0. So the spring kind of shrinks to nothing after certain oscillations, springs to its balanced position, or maybe it will kind of permanently move back and forth. That means like it's kind of as convex to form a circle. And so you can have many variations of this, and you can discuss like the stability of this problem, whether the 0, 0 state is it's a repeller or an attractor. You can discuss what happens to the physical system depending on the constants. Of course, in real life, the constants are so that every spring dies, but you can prove that here. Okay, so I stop here. We will see that example later, but before that, next week, there are a few things that I have missed in linear systems, a few details, but I don't want to go further to it. As time comes, we will look at it, because I didn't say, I always assume that there are enough eigenvectors. Sometimes they are not. And this is related to linear algebra, Jordan canonical forms, and so on. We'll talk about it next time, shortly, to finish up, and then move on to what happens in general cases. Okay? So this is it for today. Do you have any questions?
Hocam, thank you.
I thank you all. Are you still alive? Yes.
A few
Okay.
of us.
Okay.